All right, so 9.4, we're going to get into some word problems with some vectors. So when we're doing some word problems with our vectors, we're going to be talking about the velocity vector, the force vector, and then some static equilibrium. So a velocity vector is a vector that represents the speed and the direction of an object. So when we're talking about speed, we're talking about the magnitude of the vector. And when we're talking about direction, remember, that would be the same thing as the angle. Force vectors is a vector that represents the direction, so angle, and the amount of force on the object. Okay, so force, once again, is going to be the magnitude, but we're going to be talking about the force on the object instead of the magnitude, right? So they mean the same thing. So if I say find the force, I'm saying find the magnitude. Now, if we want a force is said to be in static equilibrium if the object is at rest. Okay, and the sum of all the forces acting on the object is 0. So for example, if we want static equilibrium, then we need all the vectors to add to be 0. We need all of them together to be 0 for it to be in equilibrium. So let's look at some word problems. So in 23 here, a ball is thrown with an initial speed of 25 miles per hour. So 25 miles per hour is the magnitude of this vector. It has a direction angle of 30 degrees. So our angle is 30 degrees with a positive x-axis. It wants us to express the velocity vector in terms of I and j. So if we're going to find the vector, remember on the last video we talked about to write a vector, we will do the absolute value of v cosine theta, and then absolute value of v sine theta j. So that's exactly what we're going to do. 25 miles per hour, cosine 30, and then 25 miles per hour, sine 30. Right, so it sounds a lot more complicated than it really is. We're just taking our miles per hour, which is the magnitude, and then multiplying by either cosine or sine for x and y to find the vector. So cosine of 30 is root 3 over 2. Sine of 30 is 1/2. So our vector here, vector v, is 25 root 3 over 2. I plus 25 over 2j. So that would be the vector that's representing a ball that is thrown. Right, so the ball was thrown at 25 miles per hour at an angle of 30. This is the vector that creates that. Okay, then it wants to know the initial speed of the horizontal direction. So horizontal is saying x. So to find the initial speed in the horizontal direction, we're going to take our horizontal component, which is 25 root 3 over 2. And it will be 21.651 miles per hour. Okay, the initial speed in the vertical direction, we'll take our vertical component, which is 25 over 2, which will give us 12.5 miles per hour. Okay, so it seems a lot scarier than it really is. So when we're finding vectors here, okay, we're taking the magnitude, cosine the angle, the magnitude, sine of the angle. Okay, so in 24, we have two forces act on an object. One is 60 pounds and it's due west. The other is 26 pounds with a direction angle of 120. So let's draw a picture to get an idea of what's going on. We have one that is 60 pounds and it's due west. So due west would be here. Let's call that V1. Then our other is 26 pounds with a direction angle of 120. So 120 would be around here, so let's call that V2. And we want to find the magnitude and the direction of the resultant vector. Now remember, resultant means addition. So we're going to add our two vectors together. So remember, if you think back to the very first thing we talked about was how we added vectors, our addition vector is going to be somewhere here, right? So I want to know what's the direction and magnitude of this guy. So let's first find what V1 and V2 would be in standard form. So V1 would be what? -60, 0. Now you could find that by using that the magnitude is 60, the angle is 180, and going through and using the same operations we did up here. However, you should be able to look at this and know that it's -60, 0, because we want -60 pounds up or down 0. Now V2 on the other hand, we're going to have to do some math here. So V2, the pounds is 26, so it'll be 26 cosine 120, and then 26 sine 120. Okay, and we want to find the resultant force. So I'm going to put this into my calculator. I know 120 is on the unit circle, so we could find the exact value here, but we're just going to go ahead and plug it into our calculators for our word problem purposes. So we'll have 26 cosine of 120 will give us -13, comma 26 sine 120, which is 22.517. So that is V2. V2 is -13 over 22.512 up. Okay, so there's V1 and V2. We want to find the magnitude and direction of the resultant. So resultant means addition. So we now need to add V1 plus V2. That will give us the resultant. So -60 plus -13 would give us -73. 0 plus this guy will give us 22.517. And I'm going to store this as X here so that we can work with it, because if this isn't our final answer, it didn't say to find the resultant vector, it said to find the magnitude and direction of the resultant. So now that we have the resultant, I need to find the direction, which would be tangent inverse of y over x, and the magnitude. So let's go ahead and plug that in. So we have tangent inverse of our x over -73, which gives us -17.142. However, if we look, our resultant vector was -73, 22.517. So -73, 22.517, which means it's in quadrant 2. And this is not in quadrant 2, so as you can predict, we're going to have to add 180 here, which gives us 162.858 degrees. Okay. Now to find the magnitude, we're going to do the square root of 73 squared plus 22.517 squared. So we're going to go through square root. Remember, we stored that as x, so I can just hit x there, which makes our lives really easy, which gives us 76.393, and we're going to say pounds. Okay? Pounds, pounds, pounds. All right, so not so bad. So the next problem here says that we have a small plane that is flying at a speed of 200 miles per hour on a bearing of north 55 degrees east. So let's draw a picture to get an idea of what that is. They're going 200 miles per hour at a bearing of north 55 degrees east. So if you remember, north 55 tells us that this angle right here is 55 degrees. Then we have the wind that is blowing west to east at 35 miles per hour. So it's going from the west to the east at 35 miles per hour. So we're going to call this V1 and we're going to call this V2. So V1, in order to find V1, we're going to have to do some calculations, right? So we know that they're going 200 miles per hour, so that would be the magnitude of V. So we're going to have 200 cosine, however, 55 was this angle that's created here. So this angle would be 35. Remember that these have to add to be 90 because that's a right angle. So cosine of 35 and then 200 sine of 35. Now I'm actually going to just leave them like this for a little bit until we find the resultant vector. Now V2 is going to be, well, it went from west to east at 35 miles per hour. So we went 35 and then up or down 0. So 35, 0. Now it wants us to approximate the ground speed to the nearest 1,000 miles per hour. So if I want to know the ground speed, that's asking for the resultant magnitude. So I need to find the resultant and then I need to find its magnitude. That would tell me the ground speed. Then it wants us to approximate the true course of the plane. So when it's talking about the true course, it's asking for the angle, okay, theta. So, you know, what's happening is this plane is flying, but because the wind is pushing it, right, this isn't really the path that it's flying. The path that it's flying is really going to be something like this. So we want to know what's its true speed and what's its true angle, even though this is what we think is happening. But because of the wind, it's pushing it. Okay, so we need to find the resultant, which would be 35 plus 200 cosine 35. Which would give us 198.830. You know, we're going to have to do some math with this number, so I'm going to store this as A. Okay, then we have 0 plus 200 sine 35. So 200 sine 35. Would give us 114.715, and I'm going to store that as B. So now that we have our resultant, we can find the ground speed because that would be the magnitude. So the ground speed is going to be from the magnitude. I stored this in A, I stored this in B. So of A squared plus B squared. Which would give us 229.5. Rounds up, 550 miles per hour. And then the direction will be found by doing the inverse of y over x, which is b over a, the way we stored it. If you want to store it as y and x, that's fine too. So tangent inverse of b divided by a is going to give us an angle of 29.983 degrees. Okay, however, if we're talking about airplanes and things, we should be talking about in terms of bearings. So if we got an angle of 29.983, then the bearing would be this angle right here. So I need to do 90 minus that. So our bearing is going to be north 60.107 degrees east. So because of the wind, it's really flying at an angle of 60 degrees northeast instead of 55 degrees northeast because of the wind pushing it. Okay? All right, a few more word problems. So in number 26 here, we have a weight of 100 pounds is suspended from 2 cables as shown. Okay? It wants to know what is the tensions of the 2 cables. So essentially, I don't know the force. We want this to be in static equilibrium. We need everything to just be sitting as so and perfectly. So I want to know what is the tensions, what is the force that is being pulled on each of these 2 cables in order to keep this nice and stable. So what we're going to do is we're going to create our XY axis here to go right through where our weight is being pulled. Okay, and we've got 3 vectors going here. We have this vector right here. Let's call that vector 1. Then we have this vector right here. We're going to call that vector 2. And then we have the third vector, which is the weight that's being pulled down, right? This weight, it wants to get pulled down here. And then we've got the 2 force vectors, the 2 vectors here that are pulling it up, while this one is trying to pull down. And we need all of those to just be in perfect equilibrium so that none of that happens. So we need to find these 3 vectors, and we want the resultants, if we want it to be in equilibrium, as I showed you here, then we need the resultant force to be 0. So I need to find each of these 3 vectors and then make sure when I add all 3 of them, it equals 0. So I need to figure out what is the angle of this one. Well, these are 2 parallel lines, so these are alternate interior angles. So if this is 40, this is 40. And if this is 25, this is 25, right? Because they're alternate interior angles. So V1, we don't know the magnitude, right? That's what we're trying to figure out. That's what our answer is going to be. But we know the angle is 40. So V1 is going to be the vector that's force 1. We don't know what the force is. Cosine of 40. And then force 1 sine of 40. Okay, we don't know what the force is. That's what we're trying to figure out. Now for V2, once again, we don't know what the force is, but the angle, what people always mess up here is they say the angle is 25. But remember, the angle is always created from the positive x-axis. So this is the angle here. So if we know this is 180 and this is 25, then that would give us an angle of 155, right? So really, this has an angle of 155, and then our force 2 sine 155. Okay, lastly, we have this 100 pounds that's trying to pull downwards. So this would be 0, negative 100. Right? It's not going left or right any, it's just going straight down, negative 100. So now that we have our 3 forces, we want, in order for these to be in equilibrium, we want all 3 of the vectors to be added to be 0. So we're going to do that for our x values and then for our y values. So our x values here would be f1 cosine 40 plus f2 cosine 155 plus 0 equals 0. Then f1 sine 40 plus f2 sine 155 plus negative 100 equals 0, right? So I added up these 3, I added up these 3, and we need them to equal 0. Now really, this is just a systems of equations, which we could solve by hand, but I mean, really, we're going to have to use our calculator because we don't know what cosine of 40 is anyways. So why don't we learn a new way that we can solve systems using our calculator? So our new way to solve systems using our calculator is to create what's called a matrice. And in a matrice, we're going to have our F1 component, our F2 component, and then our, I should say V1, V2. No, I had it right, sorry. Right, that's like our variable F1, our variable F2, and then our answer. So F1 is cosine of 40, F2 is cosine 155. Then we always need this to be equal to something. So if I have this is equals 0, well, that's really not there, so this equals 0. Then F1 would be sine 40, sine 155. Now, like I said, I need this to be the equal part, so I need to move this 100 to the other side, which would mean it would equal 100. Okay, so once we got all that, we're going to go to our matrice button. So matrix is right here above x to the negative 1. So we're going to go to matrix, and we want to edit this matrix, so I'm going to go over to edit. Now this is a 2 by 3 matrice, so 2 by 3 would give us 2 this way, 3 long. And then we're going to type in our values. So we've got cosine of 40, cosine of 155, and 0, sine of 40, sine of 155, and 100. Okay, so once we have all of this inputted into our matrix, we're going to go back to our home page here. We're going to go back to matrix, but instead of editing, we're going to now complete some math with this. And the button you're going to go to is RREF. It says reduced row echelon form, which tells us the answer. So we're going to go to RREF. We're going to go back to matrix. We want to do our reduced row echelon form on matrix A because that's where we put all of our information, and it gives us this matrix here. So this would be our F1, this would be our F2. So F1 is 100 pounds, and F2 is 84.534 pounds. Right, so the magnitude here is 100, the magnitude here is 84.543, and that creates everything to be in equilibrium. Okay, I'm going to leave 27 for you guys to see if you can figure out on your own.